third chapters are very, very light. And if you don't mind, some of the stuff I'm going to go through so darn quickly because it's easy. Today, I don't want to do a lot. Maybe a little bit of arithmetic. Hopefully no examples on arithmetic because it'll be that straightforward. But just vocabulary. Just vocabulary. Formal definition. A matrix is nothing more than a rectangular of things. So far in your mathematical career, they've been rectangular array of numbers. But for you and I this semester, we will replace the numbers with functions and use them as tools to solve systems of differential equations. Actually, single differential equations, but higher order, like third order, fourth order. As far as you and I are concerned, we're going to start the process off by saying, here's a matrix. It's a rectangular array of numbers. Can I give it a name? Can I call it A? And on my first row, I'll just simply list as, how about a name? How about another name? Boy, shoot, I think it's the same, darn it. Okay, subscripts. Until I get to an arbitrary column where I have an I sub, how about some J? Down to the very last entry that I'll refer to as A sub N. But I'll have a second row. I'll think of the second row as A sub 1, A sub 2, dot, 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 A sub J, dot, 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 A sub N. Oh shoot, I can't, darn it. That suggests the second row is the same as the first. How about if I double up on my subscripts? The first row consists of A sub 1, 1, 1, 2, all the way to an arbitrary 1J, and then 1N. That A sub 1J is merely the entry in the first row and arbitrary jth column. Likewise, I'll think of the second row as such, using the same logic. Now let's you and I scroll down and talk about the arbitrary of how about ith row? A sub I1, A sub I2, all the way over to the entry in the arbitrary ith row, jth column, which I'll refer to as A sub ij. All the way down to the very last column of the arbitrary ith row, whose entry are referred to as A sub in. And let me finish up. Going down to my very last row, I've got A sub, anybody? M1. A sub M2. All the way over to A sub, bless you, MJ. You guys, that's a 2, not a J. All the way down to thank you, A sub Mn. How many rows do I have? M. How many columns do I have? N. I might subclassify this as a matrix with dimension M by N. I might subclassify this as a matrix with size M by N. I'll use those interchangeably. Now, sometimes I get sick and tired of writing all this. And as a mathematician, being so lazy, I compress it enormously. And I sometimes just simply write, got a matrix of size M by N. And I can talk about the arbitrary element in the ith row, jth column. I will sometimes use that notation to represent it. It becomes very handy when it comes to some theorems I might want to prove about matrices. Now, I confess, sometimes my matrices are so darn special, they look like this. If M is equal to N, I've got the same number of row and columns. I'll get what I sometimes subclassify as a square matrix. But what if I had this square matrix? Oh, I lost my tip. You see where
got it, Randall?
Let's just talk about trajectory paths. Look at you today. What if I had a matrix where I had ones along the main diagonal? And zeros everywhere else. This is going to be such an important matrix. I'm going to use special notation for it. I'll refer to it as I. Actually, I'll do better than that. I'll refer to it as I sub n. And I'm going to think of this as my identity matrix of dimension n by n. It's my square matrix of dimension n by n. That is what I classify as my identity matrix. I can't do this today, you guys. But next week, next Monday, I'll start talking about multiplication of matrices where it becomes tremendously important, and you'll see why I refer to it as my identity matrix. Actually, take a matrix A multiplied by this, whatever multiplication means, you get the A right back. So that's like the number one in the real number system.
For those of us who haven't had college algebra in a while, are you going to review basic rules of matrices at all, or should we brush up over that?
Oh yeah, I'll review everything.
Okay.
Yes, yes. But you guys, I don't like my notation. Do you think I can change it a little bit? Because this is such a special matrix, I sometimes refer to this as a matrix whose arbitrary entry is delta psi j. Where? I think delta psi j is equal to anybody?
0, 1.
0, 1. It's going to be 1 if.
If I equals j.
It's going to be 0 if.
I is not j.
Actually, this is so important. Can I give it a name? I'm going to call this my
Kronecker?
Kronecker delta notation.
Okay.
For my identity matrix. Oh, you're yawning. Sorry. What can you say about this matrix? Anything interesting about it?
Square.
Yeah, it's a square matrix. Anything else interesting about it?
Is that a 6 at the bottom, or?
Yeah, it is a 6, not a 0.
And is it upper triangular?
Thank you. I sometimes will subclassify this as an upper triangular matrix because along the main diagonal and above it, I've got non-zero values. Well, I shouldn't say that I made a mistake. They could have been zeros. I should slow down a little bit. It's upper triangular because below the main diagonal, everything is a 0. What if they're all zeros? Any special name I can attribute to that one?
Oh, 0 matrix.
Yeah, I'd probably call it a 0 matrix of size, in this case, 3 by 3. Likewise, if above the main diagonal I had nothing but zeros, I may subclassify that as a lower triangular matrix. Who the heck really cares? Sometimes we care, particularly when it comes to determinants, which are based on matrices. Computations might become a lot easier in such a case. Since you guys have seen matrices in your past, do you remember what it means to take a scalar, a number, and multiply by a matrix? What happens?
All the entries get scaled.
All the entries get multiplied by the scalar. You guys, I don't like that. Can I restate it officially? In other words, when it comes to scalar multiplication, I think 3 times, I think C times A is like multiplying C by the matrix whose arbitrary entry is A sub ij. But to make this definition formal, for any n by n matrix A, I think what I end up getting is a matrix that's still n by n, where I've got the arbitrary ij entry in the matrix A is just that entry itself is being multiplied by C. What this says to me in English, it says that scalar multiplication of matrices is component-wise multiplication, meaning every component is being multiplied by C. Don't take that for granted. Maybe next week I'm going to change this, and when it comes to determinants, it will not be the case. So don't take it for granted. What do you think I can say about, with your knowledge of matrices, what do you think I can say about A plus B?
I don't think it's
Yeah, I don't think it's defined. It's not defined because those two matrices do not have the same size. They do not have the same dimension. I cannot legally add them. Do you think I can add A and C?
Yes.
Oh yeah, piece of cake. I think A plus C ends up being another matrix the same size, but 3, 3, 6, 5.
Negative 3. Wait,
14.
-2, 14. It's a 5 and a negative
What?
7.
It's 8 and 6. That's 14.
oh, it's a negative. I thought it said negative 2. Sorry. That's not correct. Don't listen to me.
Better?
Yeah.
Yeah.
But check this. Oh, you guys, I don't like that example either. That was too mundane. Can we be efficient? I think when it comes to adding two matrices, here's how I'm going to define the addition of matrices. If I show you what A looks like in terms of its components, show you what B looks like in terms of its components, I think this ends up being nothing more than a whole new matrix whose entries are A sub ij plus B sub ij. In other words, like scalar multiplication, I think matrix addition is nothing more than component-wise addition. It is that darn basic. Do you see how I'm saying today is such a light introduction to matrices? Nothing dramatic.
What about multiplication of matrices?
Not quite so fast.
Okay.
I'll have to slow down with that.
The first question is, why is the middle part of the equation important? The second expression. Can't we necessarily just say A plus B equals and then your component-wise?
I think it's important because I wanted to officially give you the name of the arbitrary ij entry in the first matrix, so that you see exactly what I do to it in terms of an operation.
The second question is, wouldn't you put, in the final part, wouldn't you put parentheses around the A, ij plus B ij? You just put another subscript at the end of that parentheses. I don't know if you specified. I'm not sure.
Like that.
I would say ij, but
Oh, you mean like this? You're saying you want to rewrite it as?
I meant having subscripts on the outside, but sure. I just
Well, let's do both. I don't like this one. I don't like it because I have no idea what A represents. And besides, when I first initially said, oh, I can think of A to be expressed this way in terms of components, the subscripts have to be adjoined to the A, so I know exactly what row and column it is. Even though it's arbitrary I through our jth column. So I would never want to leave it alone because now I can't bring it back to the original matrix. Secondly, this makes me nervous because it's like I'm doing something with I through a jth column on the inside and then doing it again on the outside. And so the notation here has no meaningful interpretation for me. I can't be redundant in terms of identifying what row and column I'm in.
Right, my only complaint is that you are specifying which components you're adding together, but I don't think you specify where that sum eventually goes as far as it.
See, I think quite the contrary. I think what I'm showing you, the reader, is that whatever row column I had for the entry of the first matrix is the same row and column I have for the second matrix. Therefore, I know exactly where I'm at. So I would have stopped there. Do you guys think you could do this for me?
Okay.
7.
I agree with this 15.
11. -1. -1.
I agree.
36.
I like it. So I can consider linear combinations of those matrices A, B, excuse me, A and C, my apologies, A and C, not A and B. Oh, you guys, 10 minutes. I know I've got to think so. Not a lot. If you guys don't mind, I don't have to sign any homework on this. Can I just slam out one more definition? It's just a man-made definition, nothing more. There are going to be times where it's going to become kind of important for us to take a matrix, like this matrix A. Identify its first row, which contains entries 1, 2, and 3, and rewrite the first row as the first column. Take the second row, rewrite it as a second column. Take the third row, rewrite it as a third column. I know it's not the same matrix, but I will say in English is the transpose of my matrix A. And as my formal definition, given a matrix A, whose arbitrary entry is A sub ij, that if you were to transpose a matrix, all you're really doing is interchanging rows and columns. Again, I'm speaking somewhat meaningless to you guys in class because I'm not really telling you where these things naturally pop up. I'm just saying, man, read definitions. Let's just deal with it and get used to this notation of component-wise representation.
Before we move on to transposes, you said this is merely a linear combination. What is a linear combination?
Ooh, what a good question. I'm sorry if I said that so fast. This idea of linear combinations this semester is going to be so important for you. A vector in two space. And with vectors, isn't this true? Isn't this true?
Yeah.
Isn't this true? Because my matrix can be expressed as some constant times I bar plus some other constant times j bar, I would say that my vector right here can be expressed as a linear combination of I bar and j bar. It's an extremely important phrase for you and I. To say that this is a linear combination of two other things means I can express my one item as constants times those two things and then add it together. Can I give you a heads up of how really important this is? You and I are going to study things called spaces, in particular vector spaces. And one of the questions are going to be this. Is there a seed of elements in my vector space that generates everything? Is it the case that every single element in my vector space, whatever that is a big set, is it the case that everything in there can be expressed as a linear combination of some basic items? And if that's the case, it's going to be something powerful for us. Can I show you how I'm going to make a really big circle after maybe 7 weeks in class? After about 7 weeks in class, I'm going to start talking about solutions to higher order DEs that can be expressed as a linear combination of other solutions. Meaning the I bar and the j bar as solutions to DEs are going to be the seed or the generating set for all the other solutions. And we'll have some rich language and notation for talking about solutions to DEs in that fashion with linear combinations. It's that important for us. I don't think I realized how tired I am today. Did you guys think we stopped a little early?
Yes.
I got to mosey over to I'm tired. The club thing. Anyways.
Oh, okay. Club thing.
Really good.
Yes, of course.
Are you going to have eyes contracts for us?
I'm going to work on it this weekend. Yeah.